Hey, how are you doing guys? I'm Baha and for today's video I'm gonna explain to you image classification from scratch. So let's get started. So these are objectives for today's video. So first of all we are going to work with a lower level API, and then I'm gonna show you how to make a model by using pure PyTorch code, and then we are going to simplify our model by using fastai library, and the last thing I want to give you an introduction about ResNet architecture. And here's our outlines for today's video. So we have a lot to cover today, so let's get started. So for today's video, we are going to work with MNS dataset, which is contain images of handwritten numbers, and it has two channels, black and white. So first of all, we need to grab two things. We need to grab our libraries and we need to grab our data. So for our data, we are going to use enter data method as we used before to grab a bits dataset. So here we are going to ask it to grab for us MNS dataset. And this code here is going to grab our libraries. So we are going to use the same libraries that we used in the last video, basics, vision, callbacks. So I want to remind you of them. Okay, so basics library contain a basic functionality for working with data, and vision library provide tools for working with image data, and callback library gives us an access to various fit functions. And for dataset, as I told you, MNS dataset, which is contain images of handwritten numbers, it has two channels, black and white. Today we are going to use the lowest level API. So FastAI has three APIs as I told you. So let me remind you. Okay, so the first one is the high level API, and the second one is the mid level API. Okay, and the last one is the lowest level API that we are going to use today. So in the last two videos, we used a high-level API for data loading. So if you remember the data block API that allows us to define how our data should be loaded and transformed, then it automatically creates a data loaders object that we used for training our model. And now we are going to work with this API, the lowest level API. So the lowest level API gives us a set of functions and classes that provide direct access to underlying PyTorch framework. So these functions and classes allows us to create a custom models. Also, the lowest level API is designed for advanced users who want more control over on their models and the training process. Okay, so here's a more explanation. The high-level API provides ready-to-use functions to train models in various applications. It built on top of the lower-level API, and the lower-level API provides composable building blocks. For this way, user can rewrite part of high-level API or add particular behavior to suit his needs. Okay, so to work with the lower-level API, we need to make our data source. So to make our data source, we need to define three things. First of all, we need to define our file names, and then we need to make our BIL object, and then we need to define the way that we can split our data with it. Okay, so as you can see here we are going to define our file names by using getImageFiles method, and we pass it our path that we defined in the code above here. So it will make for us a list of all file names that we have in our dataset. So if we print the first item in items, it will print the path of the first image. So here's the path of the first image, and here's the name of the image. Okay, and here we are going to path our first image to a BIL image black and white, and this object offers several standard procedures for image manipulation. This include pre-pixel manipulations, masking and transparency handling, and much more. And here we are going to show our first image. Okay, and here we are going to define an object that we are going to use to split our data. So in our task here, we are going to use a grandparent splitter, which split our data into two datasets. The first one is the training data, and the second one is the testing or the validation data. Okay, and here's more details about the grandparent splitter. As I told you, it splits our data into training and validation sets based on the grandparent folder of each file. So what this means? So each folder represents a class or category, and each folder had subfolders containing images or other files. Then the grandparent splitter will split the data based on the top level folder. For example, if we have a dataset with two classes, cats and dogs, and each class contains subfolders containing images, then the grandparent splitter will split the data based on whether each image belongs to cat's class or dog's class. Now we are going to make our data source. So as you can see here in the code, to make our data source, we need to pass it three things. The first one is our items that we defined earlier in the code, and the second one is our transforms. So by transforms, I mean we need to define how we want our inputs to come in and how we accept our y's to be formed. So here we pass it two lists. The first one says that when we grab our x's, we are going to use bil image black and white dot create to open our file names, and the second one says that whenever we are dealing with our y's, we want to use a parent label, which is our folder, along with categorize, which is make everything into categories for us to classify with. And the last one here, we are going to pass it our splitting method, which is a grandparent splitter that we defined above. Okay, so here we are going to look at an item in our data source by using a show at method. So we pass it our data source and whether we want these items to be from our training dataset or our validation dataset. And the last thing, we need to define the index of that item. So here we pass it the index of 3, and here's the image of that item. Okay, so now everything from here we need to define it by hand, because under the service everything is converted to a tensor. And then we are going to apply our transforms and then pass it to our model. So why we need to do these transforms? Because three things. The first one is to ensure our images are all in the same size, and then to make sure our outputs are all tensors. And the last thing is to do some augmentations on our images. Okay, so for our transforms, we are going to make our item transforms and our batch transforms. So our item transforms, these transforms are applied to each image in our dataset after it has been loaded from disk. Okay, so we are going to convert our images to tensor, and then we are going to crop them and parent them to be 34 times 34, and then we are going to randomly crop them again to be 28 times 28. So these for our items transforms. And for our batch transforms, so these transforms are applied to a batch of images after they have been collated into a single tensor. So we are going to use a CUDA, which is enables to GPU usage, and then we are going to convert our tensors to be float. So we are going to use a int to float tensor method, and then we are going to normalize our data by using a normalize method here. So here we are going to bunch our data source. So to bunch our data source, we need to define the number of batch size, which is 128, and then we are going to pass it our item transforms. So we pass it to after item, and then we are going to pass it our batch transforms, which we pass it to after batch. Okay, so now So here's the more details about our item transforms and our batch transforms. So our item transforms apply to each individual item in a dataset after it has been loaded from disk. These transformations are typically used to pre-process the data and make it more suitable for training a machine learning model. And our batch transforms apply to a batch of items after they have been collated into a single tensor. These transformations are typically used to normalize the data and make it more consistent across batches. So after we make our item transforms, then we can make our batch transforms. So item transforms is made first, and then we made our batch transforms. Okay, so here, as I told you, to bunch our data source, we need to define three things. The first one is a batch size, and then we need to define our item transforms, and then we need to define our batch transforms. Okay, so for now, we need to see what our model will expect. So we are going to use one batch method, which is returns to us our input of our batch and our output of that batch. So we are going to define two variables here, xb that corresponds to our inputs and yb which corresponds to our output. And here we are going to see our shape of our inputs and our outputs. So the first one here is correspond to our input shape. 128 here is corresponds that we are have a 128 images, and this one here is tells us that our images have one channel, which is a black or white, and 28 and 28 here is corresponds to our image size. So our images have 28 times 28 pixels. Okay, so for our output shape here we have 128 labels, and databunch.c here it tells us how many labels that we have. So we have 10 labels. Now we are ready to build our model. So our model is made up of convolutional layer, batch normalization activation function, and flattening layer. So let's go with the first layer, which is a convolutional layer. So to understand it, we need to look at this example here. So imagine a flashlight that's shining over the top left of an image, which covers a 5 by 5 section of pixels at one given moment. This flashlight then slides crosses our pixels at all areas in the picture. This flashlight is called a filter, which is called neuron or kernel, and the region it's currently looking over is called a respective field. So what is this filter? So the filter is an array of numbers called weights or parameters, and the depth of filter must equal the depth of our input image. So in our case, our input image has one channel, so the depth of our filter must be equal to 1. For a color images or RGB images, the depth of the filter must equal to 3. So now once this filter is being moving around the image, it's multiplying the value inside the filter with the original pixel value of our image, which is called a element-wise multiplication. These are then summed up into a individual value, which is a representation of just the top left of our image. Now we repeat this until every unique location has a number, and we will get what is called a activation or feature map. So let's make it more clear. Okay, so let's imagine here is the image and we need to apply a filter on that image. So what this filter is going to do is going to look at this part here and is going to do some competitions, which is a element-wise multiplication. So it's going to multiply the value inside this filter with the original value in this part here, and is going to sum up all of these values to individual value. So after it's finished, it's going to repeat itself. So it's going to look at this part here and do the same computations until it covers all the pixels in the image. Okay, so let's go with my notes. So a convolutional layer used for feature extraction and image classification task. It performs a 2D convolutional operation on an input image and applying a filter to extract a features. So in code, we are going to make a convolutional layer. So we are going to borrow a PyTorch NN conv2d, which is here, NN conv2d. And we are going to pass it our kernel size, which is our filter. So our filter is going to look at 3 by 3 pixels at once. And then we are going to pass it our stride and padding, and we pass it ni and nf. So what is ni? So it's equivalent to the depth of the filter. In our case, the ni is equal to 1 because our input image have one channel, and nf is equal to how many filters we will be using. Okay, so let's go with the second layer, which is a batch normalization layer. So it's used to normalize the output of the convolutional layer. So it helps to improve the model performance and reduce the overfitting by scaling and shifting the output of the previous layer. So in code here, we are going to define our batch normalization layer. So we pass it the output of the previous layer, which is nf, which is the output of our convolutional layer, and we are going to borrow a batch norm 2D from PyTorch. And then we are going to define our activation function. So in our case, we are going to use a ReLU. So if you don't know what is activation function is, so it's apply a nonlinear function to the output of the previous layer, which is a batch normalization. And a ReLU is the most commonly used activation function in deep learning, which is simply set all negative values to 0 and leaving the positive unchanged. And here is the formula of it. So it's a max between 0 and x. So if x is greater than 0, so it will be the same. We unchange it. And if the x is less than 0, so we make it 0. And here's the plot of ReLU. And in this code here, we are going to define our activation function, which is our ReLU. So we are going to borrow a ReLU from PyTorch. And then let's go with the last layer, which is a flattening layer. So it's used to flatten the output from the previous layer before passing it to a fully connected layer or dense layer. This layer is often used after the convolutional and batch normalization layer to convert the output tensor into a one-dimensional vector. Okay, so in short, convolutional layer extracts feature maps from the input image. Batch normalization layer normalizes and scales the output from the convolutional layer. Flattening layer converts the high-dimensional feature maps into one-dimensional vector. Okay, so now in code we are going to make our model. So our model is consisting of 5 convolutional layers. They are going from 1 to 32 and then go back to 10. And we are going to borrow nn.sequential from PyTorch, which says that run this particular code in this sequential order. Okay, so let's explain our code here. So this code here is going to define a neural network by using nn.sequential from PyTorch. So the first layer is a convolutional layer with 1 input channel and 8 output channels. And then we are going to pass our output from our convolutional layer to our batch normalization layer. So we pass it 8 channels. So this layer is going to normalize our output to improve the model speed. And then we are going to apply our ReLU, which is our activation function. And then all of these layers here are the same, but instead we are changing the number of input and output channel. So as I told you, our model is consisting of 5 convolutional layers. They are going from 1 to 32 and then go back to 10. So as you can see here, the first layer is going from 1 to 8, and the second layer is going from 8 to 16, and the third is going from 16 to 32. So now we are going to go back to 10. So the fourth layer is going from 32 to 16, and the fifth one is going from 16 to 10. Okay, and the last layer here is our flattening layer, which is convert our output tensor into one-dimensional vector. Okay, so here's more details. So as I told you, this code defines a neural network model by using PyTorch NN.sequential model. The first layer is a convolutional layer, which is conv here with 1 input channel and 8 output channels. This layer applies a set of filters to the input image to extract features. And the second layer is a batch normalization layer, BN. So here's that normalize the output of the conv layer to improve the training speed. And the third layer is a ReLU, which is our activation function. The fourth and fifth layers are similar to the first two, but with different number of input and output channels. And finally, these are our flattening layer, so that flattens our tensor into one-dimensional tensor, which can be used as a fully connected layer. Okay, so now we are going to make the learner. So our learner is different from our vision learner that we saw in the last video. This learner allows for any model, any loss function, and any metric. So to make it, we need to pass it our data bunch, our model that we defined here, our loss function, and the last thing we need to pass it our metric. So here we are going to use the accuracy metric. And learn the summary method here is allows us to look at the exact output shapes of our model. Okay, so here we are going to find our optimal learning rate. So as I told you in the last video, we are going to use this method here and this method here, plot our learning rate and our loss function. So we assume that our learning rate is 10 to the power -1 because our loss function is going to be pretty small. So here we choose it and we run our model with 3 epochs. Okay, so let's simplify our model. So we are going to use a conv layer from fastai, which is a function that takes an input tensor and applies a set of filters to it. This function also includes other operations such as padding, stride, activation functions like ReLU and patch norm 2D. So here we are going to define our conv2. So we are going to use a conv layer from fastai, and then we are going to pass it our ni and nf, and as we made before, and then we pass it our stride. So this code here, instead of making our convolutional layer and then pass our output to the batch normalization layer and apply our activation function, this code here is going to make all of these for us. So what we need to do is to pass it our convolutional layers and our input channels and output channels, and then it takes our output from our convolutional layer and pass it to a batch normalization layer and apply an activation function for us. So here we define our 5 layers. So the first one, as I told you, is going from 1 to 8, and the second one from 8 to 16, and then we are going to 32, and then we are go back to 10. And the last layer, which is a flattening layer, which is convert our output tensor into one-dimensional vector. And here we are going to define our learner as we talked before. So we pass it our data bunch, our model, which is our net here, our loss function, and our accuracy metric. and then we are going to train it by 3 epochs. Okay, so for now let's talk about ResNet architecture. So ResNet architecture contains two conv layers wrapped into one. So ResNet architecture works by having two of these conv layers wrapped into one. So to make it, we need to create two conv layers, and here in the code, so in the constructor part here, we create two conv object, conv1 and conv2, with nf as our input and output channels. And for forward method here, it takes an input tensor x, and then is going to apply these two convolutional layer to it. So the output of the first layer of the conv1 layer is fed into the second layer, which is a conv2 layer, and the output of these two layers is added to our input tensor x. Okay, so here's the code again. So in the constructor, two conv layer objects are created with nf as input and output channels. The forward method of ResNet block class takes an input tensor x and applies the two convolutional layers to it. The output of the first convolutional layer is fed into the second convolutional layer, and the output of this is added to the original input tensor x, creating a residual connection. Okay, so for now, let's remake our model by using our res block. So the code is exactly the same, except we incrementally adding this res block here. So we are going to define our convolutional layers and then pass our res block the output of each of these convolutional layers. So this res block here is going to take the output of the previous layer, which is the output of this convolutional layer. Okay, so here's the code. And our net, which is our model, is take our simple model that we defined earlier and convert it to a complex one by adding this res block. Here we are going to make our code simpler by define our conv and res layer, which is combine our conv2 and our res block into one by using nn.sequential. So here we define our conv2 layer and pass it our input and output channels, and our res block layer is going to take the output of this layer. And here's the code, so it's simpler than the previous one. And here we're going to make our learner and find our optimal learning rate and train our model with 3 epochs. And here we are going to export our learner because we are going to work on a deployment. So that's it for today's video.